The coherent processing system can have an optional global interrupt controller. This section covers its configuration and use. The GIC handles the distribution of interrupts between the processor elements in a multi-core cluster. A processor element is a virtual processor element or VPE in a multiprocessor system made up of MT cores, or a single processor in a multiprocessor system made up of single non-MT cores. Your system can have up to 256 external interrupt sources. The GIC distributes interrupt sources between the available processor elements in the system. You can configure it to connect any interrupt source to any interrupt input, which can be an interrupt pin, an NMI pin, or a yield qualifier pin on an MT core. It allows any processor element to interrupt any other processor element. It routes local interrupts such as the timer, watchdog, GIC count and compare, performance counters, and software interrupts to an interrupt pin, NMI, or yield qualifier on the local core. It is backward compatible with the legacy and vectored interrupt modes, and it is able to integrate interrupt messages from peripherals such as HyperTransport and PCI Express. To get started using the global interrupt register, you must first know where they are in the memory map. The address of the GIC registers should be programmed by the boot code in the GCR GIC base address register. This register is located within the global configuration register block at offset 80 hex. As you can see from the table, the address is on a 128K boundary, so the lower 7 bits will always be 0. This leaves space for additional information in the register. The GIC EN field controls the enabling of the GIC. Once the boot code configures the GIC, it should enable it by setting this bit. Starting at the GCR GIC base address mentioned in the previous slide, the GIC address space is accessed with uncached load and store commands. For each load or store command, the hardware supplies the physical address and the number of the processing element of the register. The processing element number is used as an index to reference the appropriate subset of the instantiated control registers. By using the processing element number information, the hardware writes or reads the correct subset of the control registers pertaining to the local processing element, so your software does not need to explicitly calculate the register index for the local processing element. It's done entirely by hardware. The GIC is divided into sections. The first section starts at the base address of the GIC. This section is where the external interrupt sources are registered, masked, and assigned to particular processing elements and interrupt pins. This section is used by all processing elements. The next is a local section, which starts at the base address plus 8000 hex. This is the section in which interrupts local to the processing element are registered, masked, and signed to a particular interrupt pin. The local processing element can access the local registers of another processing element by using the other local address space. Software must write the other address register before accessing these address spaces. The value of this register is used by hardware to index into the appropriate subset of the control registers for the other processing element. An additional section called the user mode visible section is used to give quick user mode read access to specific GIC registers. The use of this section is meant to avoid the overhead of system calls to read the GIC resources, such as the counter registers. I'm going to start with the shared section of the global interrupt controller. This section of registers can be accessed by all processing elements while in kernel mode. Most of the registers in this section are used to configure the global interrupt controller. Usually you would do this configuration in your boot code using processing element 0. In most cases, the other processing elements only access these registers for status information. The names of these registers in this section all start with GIC_SH to indicate they are Global Interrupt Control Shared Section registers. The configuration register is the first register in the shared section located at offset 0. It contains configuration information and a control bit. The count stop bit is a control bit that will stop the GIC counters. The count bits field encodes the number of bits in the GIC counter. In the current implementation, there are always 64 bits in the counter, so the count will always be 8. I'll cover the counter registers a little later in this section. The boot code will use num interrupts field to determine how many external interrupt sources there are. Interrupt sources are configured in the core in groups of 8. This field tells you how many groups of 8 plus 1 the core has. 0 would indicate one group of 8, 1 would indicate two groups of 8, and so on. PVPE tells you how many processing elements there are in the system. The GIC revision register has two fields. The major revision reflects the changes from one product to another. The minor revision field reflects the changes from one release to another. You can configure the polarity of the interrupt source by using the polarity registers. There are enough registers instantiated for the number of interrupt sources in the coherent processing system. As I have gone over in the Gic configuration register slide, the num interrupts field can be decoded to give you the total number of interrupt sources. Each bit in each polarity register controls a source. To find out how many polarity registers you have, you divide the total number of interrupt sources by 32, always rounding up if there's a carryover. Interrupt source 0 is bit 0 of the first polarity register located at offset 100 hex. This register will control the first 32 interrupt sources. The next register will control the next 32 interrupt sources, 32 through 63, and so on. There are other registers I'll cover next that determine the interrupt type, which can be level, single edge, or dual edge sensitive. If the interrupt type is level sensitive, then setting the corresponding source bit to 1 will configure the source to active high, and setting it to 0 will configure it to be active low. If the interrupt is single edge sensitive, then setting the corresponding bit to 1 will configure the source to rising edge toggle, and setting it to 0 will configure it to falling edge toggle. You can configure the type of the interrupt source by using the trigger registers. There are enough trigger registers to cover the number of interrupt sources implemented. The calculation of the number of registers is the same as for the polarity registers. If a bit is set to 0, the interrupt is level type. If the bit is set to 1, the interrupt is edge type. The next slide will show you how to configure it to single edge or dual edge. If you configured a source to be edge sensitive, you can further configure it for single edge or dual edge using the dual edge registers. As was the case for the previous two registers, there are enough dual edge registers to cover the number of interrupt sources implemented. The calculation is the same as it was for the polarity registers. If a bit is set to 0, the interrupt is single edge. If the bit is set to 1, the interrupt is dual edge. The right edge register is used to support interprocessor interrupts. If you want to send an interrupt to another processor, the interrupt source must be configured to be single or dual edge sensitive. Polarity does not matter. Setting the interrupt will always activate it. The RW field determines if you are setting or clearing the interrupt. To send an interrupt, set this bit. To clear an interrupt, clear this bit. Along with the RW field, you need to set the interrupt field to the interrupt number to send the interrupt to. The processor that receives the interrupt will clear the RW bit and set the interrupt field to the interrupt number to clear the interrupt condition. To set up the system for interprocessor interrupts, you would determine which interrupt sources to use for this purpose and which processor should enable a specific one of those interrupts. In this way, each interrupt can be programmed for a specific processor, or any number of processors could be interrupted by a single interrupt. The boot code section of this class gives a coding example of setting interrupts 24 through 39 for the purpose of interprocessor interrupts. The next three register groups control the enabling, disabling, reporting of enabled state, and reporting pending interrupts. As with the polarity, trigger, and dual edge registers, there are enough instantiated registers for each group for the number of interrupts in the coherent processing system. The table shows you the address offset ranges for each register group. The reset mask register is a write-only register. Use it to disable an interrupt by setting the bit that corresponds to the interrupt. The set mask register is also a write-only register. Use it to enable an interrupt source by setting the bit that corresponds to the interrupt. When you write to the set or reset registers, only the bits you set are affected. So if you want to disable interrupt source 3, you would just set bit 3 of the first reset register, and only interrupt source 3 would be affected. To check to see if an interrupt source is enabled or disabled, you read the mask register. Any set bits indicate that the corresponding interrupt is enabled. To check to see which interrupts are active, you read the pending register. Any bits that are set indicate the corresponding interrupt is active and waiting to be processed. These next slides cover the mapping of an interrupt source to an interrupt pin on a specific processor. The MIPS architecture defines 2 software interrupts and 6 hardware interrupt pins for each processor. The global interrupt controller can map any interrupt source to any hardware interrupt pin on any processor. In addition, any interrupt source can be mapped to the non-maskable interrupt pin or on an MT system to any of the yield qualifier pins. The map to pin registers are used to map to a hardware interrupt pin on a processor, and the map to VPE registers are used to map to the interrupt source on a particular processor. The map to pin register is used to map an interrupt source to an interrupt pin. For every interrupt source, there is a 32-bit map to pin register. The address of the register that corresponds to any interrupt source is the GIC base address plus 500 hex plus the interrupt source number times 4, because the addresses are on word boundaries of 4 bytes each, plus the offset of the GIC. There are 3 bits that control the type of pin that is assigned to the interrupt source. While there is nothing to prevent you from setting more than one of these bits, only one of these bits should be set. The map to pin bit means you will be mapping to an interrupt pin on the processor you will be assigning in the map to VPE register. The actual pin or interrupt vector will be set in the map field of this register. The map to NMI bit will map the source to an NMI input of the processor. The map to YQ should only be used if your multi-core is made up of multi-threaded processors. In that case, it will map the interrupt source to one of the yield qualifiers of a VPE. The map field setting depends on whether you are mapping to a pin or a yield qualifier. For pin mapping, it is simply the pin number you are assigning the interrupt source to. If you're using EIC mode, then it is the vector number between 0 and 63. For a yield qualifier, it is simply the number of the yield qualifier pin that you want this source to activate. Each interrupt source can be routed to any processor or a VPE on a multi-core system. This is done by programming the global interrupt mapped to VPE registers. There are 2 of these registers for each interrupt source, so you can map processing elements from 0 to 63. Each of these pairs is located on a 32-byte boundary. The first pair for interrupt source 0 is located at offset 2000 hex in the GIC address space. The second pair is at offset 2020 hex, and so on. On a multi-core system made up of single cores, we are currently supporting 4 cores, so only bits 0 through 3 of the first register in the pair can be used. On a multi-core system made up of multi-threaded cores, you can have 4 cores with 2 VPEs each. So in this case, you can have 8 processors. For this type of core, bits 0 through 7 of the first register are used. You can map an interrupt source to more than one VPE or processor. In that way, they can all synchronize on an interrupt. This is useful for processor-to-processor interrupts. Software would need to control the VPE that did the housekeeping if needed for the interrupt. If you are using EIC mode, you must set the register set to use for each interrupt source. It is not an initialized register, so if your system does not have shadow register sets, you must set this field to 0. Note that the slide and others, offset L is the offset of the address segment of the current executing processor, and offset O is the offset address of the segment of the processor whose ID is in the VPE other addressing register. In summary, I have shown you how to set up the interrupt type by using the global polarity, trigger, and dual edge registers, and how to send and clear interprocessor interrupts using the right edge register. How to set the interrupt state using the set mask to enable and the reset mask to disable interrupts, and how to detect the interrupt state using the mask and pending registers. How to map the external interrupt sources using the map to pin and map to VPE registers. Here is the big picture summary of the registers for external interrupts. The local and other sections are used to process any interrupts which are generated locally within the processor. This includes the watchdog timer, software interrupts, local performance counters, and the count and compare interrupts. All of these interrupts can be routed to an interrupt pin on the local core. A local shadow register set can be mapped to an interrupt source. There are 2 identical sections. The local section is the registers for the processor that is executing the code. The other section is the section of another processor. By using the other section, one processor can program all the other processors. One thing must be noted here: the system software needs to make sure that only one processor at a time is using a group of registers. This is usually not a problem because most accesses of these registers are done at boot time. I will cover the boot code for a CPS in another section of this class. The other address register is used to select the processor's registers that are accessed through the Other Registers Map section. The processor number is written to the lower 16 bits of this register. If you are running on an MT system, this would be a VPE number. There are three types of counters available to each processor. The CP0 counter that is within each processing element and is not shared by any other processing element. When a value is set in the CP0 compare register and then the count register reaches that value, an interrupt can be generated. This is covered in detail in the Programming a MIPS Core class. This interrupt generates a timer interrupt. As you will see in the upcoming slides, the timer interrupt can be enabled and mapped by the GIC to an interrupt pin within the local processor. The interval timer is very similar to the CP0 counter. It too works with a count and compare register. The difference is that the count register is global to all processors, whereas the compare registers are local to each processor. Both of these registers are part of the GIC, and I will cover them in this class section. The interval timer generates a compare interrupt, which, like the timer interrupt, can be enabled and mapped by the GIC to an interrupt pin within the local processor. The watchdog timer is a countdown timer. It's meant to be a liveliness timer to tell if the processor has gotten stuck. It needs to be kept from timing out by the software running on the local processor. When the count in the watchdog register reaches 0, it generates a watchdog interrupt. Like the other two timers, the watchdog interrupt can be mapped by the GIC to an interrupt pin within the local processing element. Typically, this would be the NMI pin. For the interval timer, the count is kept in a two-register set that counts in the units of the GIC. Usually this is in cycles, but it is implementation specific, so you should check with your system designer to make sure what frequency the counter counts at. Since the number of count bits is fixed at 64, the low counter overflows and increments the higher counter. This is a read-write register, but you should always disable the counter by setting the count stop bit in the GIC configuration register before you write to it. Note again, this is a shared register within the GIC. The compare value is set in a two-register set within the local section of each processor. When the GIC shared counter reaches the value in these registers, a compare interrupt is generated. Note again that the compare registers are per processor. The watchdog timer configuration register configures the actions of the watchdog timer. If the watchdog reset bit is set, it indicates that this processor's watchdog timer has expired and has generated a system-wide reset signal. This bit can be cleared by writing a 1 to it. The watchdog timer interrupt bit indicates that this watchdog timer has generated an interrupt. This interrupt can be cleared by writing a 1 to this bit. If the wait mode control bit is set to 1, the watchdog timer will continue to count if the processing core is in low power mode. Otherwise, the watchdog timer will stop decrementing when the processor enters low power mode. If the debug control bit is set to 1, the watchdog timer will continue to count if the processor core is in debug mode. Otherwise, the watchdog timer will stop decrementing when the processor enters debug mode. The type field determines what happens when the watchdog reaches 0. If the type is set to 0, the processor stops and asserts a watchdog interrupt signal. If it is set to 1, the watchdog will reset to the initial count and start decrementing again. If it reaches 0 on the second try, then it will assert a system-wide reset signal, SI reset. If it is set to 2, it will assert a watchdog interrupt, reload the initial count, and start decrementing again. The WD enable field is used to enable or disable the watchdog timer or reload the initial count. Setting this bit to 0 disables the timer. Setting this bit to 1 enables and reloads the count set in the watchdog timer initial count register. To reload the count to an already enabled timer, all you need to do is set this bit to 1. The watchdog timer is a 2-register set. The watchdog count register is a read-only register that contains the decrementing count of the watchdog. If the count register reaches 0, it will take the action depending on the type set in the watchdog configuration register. The watchdog initial count register is set by software with the number of counting elements to count down. Writing to this register will set the value in the watchdog count register. The local interrupt control register contains 4 state bits that correspond to the routability of the 4 local interrupts, which are the fast debug channel interrupt, software interrupts, performance counter, and timer interrupts. These bits are preset at core build time. If the bit is set, the corresponding interrupt is software routable. If the bit is not set, the interrupts would be hardwired to one of the hardware interrupt pins. Which pin they are hardwired to is implementation dependent. The EIC mode bit is the only writable bit. It controls the external interrupt controller mode of the core. Setting this bit will set the processing element to the external interrupt mode. The next 4 slides all deal with the local processor or a VPE on an MT system's interrupts. This register is the interrupt pending register. This is a read-only register that will tell you if an interrupt is pending for one of the local interrupts, regardless of whether or not the interrupt is enabled. The local interrupt mask register is a read-only register that reports the enabled status of the local interrupt. If an interrupt bit is set, the interrupt is enabled, and if the interrupt occurs, it will interrupt the processor or a VPE on an MT system. The interrupt mask register is a write-only register. Setting an interrupts bit to 1 will disable the interrupt, and the processor will not be interrupted if this interrupt is activated. But it will still show up in the interrupt pending register as a pending interrupt that you could poll for. The local interrupt set mask register is also a write-only register. When an interrupt bit is set, the interrupt will be enabled and will generate an interrupt when the interrupt is activated. For every local interrupt, there is a 32-bit map to pin register as shown in the table. This allows the local interrupt to be mapped to an interrupt pin of the local processor if it is routable in your core. There are 3 bits that control what the interrupt source is routed to. While there is nothing to prevent you from setting more than one of these bits, only one of these bits should be set at a time. The map to pin bit will map the interrupt source to an interrupt pin of the processor. The actual pin will be set in the map field of this register. The map to NMI bit will map the interrupt source to the NMI input of the processor. The map to YQ should only be used if your multi-core is made up of multi-threaded processors. It will map the interrupt source to one of the yield qualifiers of the VPE that is set in this map field. The map field setting depends on if you are mapping to a pin or a yield qualifier. For pin mapping, it is simply the pin number you are assigning the interrupt source to. For a YQ qualifier, It is simply the number of the YQ pin that you want this source to activate. In summary, I have shown you how to set the interrupt state using the set mask to enable and the reset mask to disable interrupts, and how to detect the interrupt state using the mask and pending registers. How to check the local interrupt control register to see if routing or mapping is possible and enable EIC mode. Then route the interrupts to a pin, NMI, or yield qualifier for an MT system. The core local identification register identifies the processor that is executing the code that is reading this register. It is also the number the hardware uses to locate the specific group of local registers for this processor. If you are using EIC mode, you must set the register set which is used for each interrupt source. This is not an initialized register, so if your system does not have shadow register sets, you must set this field to 0. There is one of these registers for each of the 64 EIC interrupt vectors. The GIC counter is the only register available in user mode. It is an alias of the GIC shared counters. All other registers are only available in kernel privilege mode. Additional information can be found in the MIPS 32, 1004K, 1074K, interactive, or proactive coherent processing system user manuals. Thanks for watching.